So let's have this challenging problem to reinforce the concept on three-moment equations. So this problem has support settlements. By three-moment equation, calculate the vertical reactions at B and C and the moment reactions at D. Also compute the slope at A and B. E is 200 gigapascals, moment of inertia 200 times 10 to the 6 mm to the fourth. Support settlements at A 20 mm, B 15 mm, and at C 10 mm. So here is the given figure. And moment at A is negative 30 times 3, so it is negative 90 kilonewton meter. So take note that for EAB, the moment of inertia is 1.5 I, where I is 200 times 10 to the 6. For BC 2I, and for CD it's just I. So these are the settled supports at A, at B, and at C. And this is the expected elastic curve, approximate. So that's 20 mm, 15 mm, and 10 mm. So let's have three-moment equation on span ABC. So negative 90 times 8 over 1.5. Remember, MA times span AB divided by I 1.5 relative value plus 2 times MB quantity 8 over 1.5 plus span BC, which is 5 over 2. So 2 times MB quantity 8 over 1.5 plus 5 over 2 plus moment at C times 5 over 2. Then the value of 6 area 1A over I1L1. So we need to evaluate by integration. Let's have a strip. And it is 20 dx for the differential P. We will call this distance x, and therefore this distance is not important. So that is 20 dx, and the value is integral. The range, the variation of x is from 0 to 6, and it is differential P A, which is 2 plus x, distance of strip, centroid of strip from the left, 2 plus x, all over L, which is 8, then I is 1.5, so 8 times 1.5, then quantity L square, 8 square minus A square, where A is 2 plus x. So plus integral 0 to 6 of 20 dx times 2 plus x all over L times I 1.5, quantity L square minus A square. So again, dP 20 dx. So 6 area 1A over I1L1 means we have to consider A from the left, moment of area supposedly from the left. So P dP 20 dx, A is 2 plus x, that one, all over L, then all over I, which is 1.5, then quantity L square minus A square. So this is A. Then plus 6 area 2B over I2L2. So we have to consider another strip here. So call this X. And therefore this distance is 3 minus X. And the height of the strip is taken from similar triangles. W as to X equals 24 as to 3. 24 as to 3 is 8 times x, so that's why the height of the strip is 8x. And therefore, this differential force is 8x dx. And that's 3 minus x. So that is B. So integral of differential P, 8x dx, B, quantity 3 minus x, all over L, 5I, 2, quantity L square 5 square minus B square 3 minus x square. So plus integral 0 to 3 of 8x dx, 3 minus x over 5 times 2, quantity 5 square minus quantity 3 minus x square. or dp b over l I, because it is 6 area 2 b over I2 L2. So that's why we have to consider the I, then L square minus B square. Then equals 6 EI. So 6 times EI is 40,000. So 20 times 10 to the 6 kilopascals. G is 200 gigapascals. So that's sorry, 200 times 10 to the 6 kilopascals. Then moment of inertia 200 times 10 to the 6 mm to the fourth. So that's why we divide 1000 to the fourth to make it meter to the fourth. So it is 40,000 kilonewton meter square. So equals 6 times 40,000. Quantity HA is negative 0.005 over LAB, which is 8, plus HC, which is positive 0.005 all over LBC, which is 5. Y is HA negative. The reference is horizontal line through B. Remember, horizontal line through B on the elastic curve. And since A is 5 mm below that horizontal line, that's why it's negative. And this is L of AB. While C, support C, although it's settled, is 5 mm above the horizontal line, reference horizontal line through B. So that's 5 mm. 15 minus 10 is 5 mm. So it is above. That's why it's positive 0.005 over LBC, which is 5. So simplifying, the value of this integral is 1,500. This integral is 80.28. The value of this right side is 90, positive 90. And take note, we have negative 90 times 8 over 1.5 here. So 90 minus 80.28 minus 1,500 plus 90 times 8 over 1.5 should be simplified at the right side. So this is 47 over 3 MB plus 2.5 MC equals, the simplified value at the right side is negative 1010.28. So call that equation 1. We then apply 3-moment equation on span BCD. So we transform D to be from fixed to interior pin, then extend with interior pin where moment at D prime is 0 and span DD prime is negligible. So MB times 5 over 2. The span is 5 and the moment inertia is 2 plus 2 times MC, quantity 5 over 2 plus 6 over 1. The moment of inertia for CD is 1 plus MD times 6 over 1, or simply MD times 6. Then the value of 6 area 1A over L1 is same integral here, this one, except that A, we replace 3 minus x by the distance of the strip from B, which is 2 plus x this time. And we replace this by 2 plus x. The rest is the same. So plus integral 0 to 3 of 8x dx, 2 plus x over 5 times 2, quantity 5 squared minus 2 plus x squared. Then for 6 area 2b over I to L2, I is just 1, so we have 2 loads here. So 25 times 4 over 6, quantity 6 squared minus 4 squared. For the 30 kilonewtons, 30 times 2 over 6, quantity 6 squared minus 2 squared. B is 2 for the 30 kilonewton load. So the value of the integral is, so equals 6 times 40,000. The reference horizontal line this time is through C. Then B is 5 mm below the horizontal line through C. So it is negative 0.005 meter again over 5. The span BC is 5. While point D is above the horizontal line through C by 10 mm. So plus 0.01 meter, 10 mm over span CD, which is 6. So simplifying, The value of this integral is 108.72. The value inside this quantity here is 1960 over 3. The value of the right side is 160. So 2.5 MB plus 17 MC plus 6 MD equals 160 minus 1960 over 3 minus 108.72. So 2.5 MB plus 17 MC plus 6 MD equals negative 45154 over 75. Call that equation 2. Then for span CD D prime, so we have MC times 6 over 1 or MC times 6 plus 2 times MD quantity 6 plus 0. Span DD prime is negligible length plus moment at D prime 0 plus 6 area 1A over L1. So because the loadings have different values, so for 25 it is 25 times A, which is 2 over 6 quantity 6 square minus 2 square. For 30 kilonewtons, 30 times 4 over 6 quantity 6 square minus 4 square. While the value of 6 area 2B over L2 for span DD prime is 0. There's no load in DD prime. Then equals 6EI. The reference horizontal line this time is D and C is 10 mm below, so negative 0.01 over 6, while HD prime is 0 because D prime is on the same level as D. So 6 times 40,000 quantity negative 0.01 over 6 plus 0. So the value of these quantities inside these braces, this brace is 2000 over 3. The value of the right side is equal to negative 400. So simplifying, 6 MC plus 12 MD equals negative 3200 over 3. Call that equation 3. Solving the three equations simultaneously, so we have MB equals negative 65.571 kilonewton meter, MC equals positive 6.801 kilonewton meter, and MD equals the required negative 92.289 kilonewton meter. So for the slopes at A and B, as well as for the slopes at A and B, let's have that on the next slide. So let's now have the moments transferred here and the figure. So moment B was negative 65.171 kilonewton meter, moment C positive 6.801 kilonewton meter, and moment at D negative 92.289 kilonewton meter. So let's compute reactions at A, B, C, and at D. So moment at B, negative 65.571. So it should be clockwise at just to the left and counterclockwise just to the right, because for positive moment it should be counterclockwise for just to the left and clockwise just to the right. So for moment C, it should be, because this is positive, so counterclockwise just to the left, clockwise just to the right. And for moment D, it is clockwise just to the left. So we have RB left and RB right for reaction at B, RC left and RC right for reaction at C. Let's compute for these reactions. So RB left times 8. So summation moment considering AB, RB left times 8, moment arm 8, plus 30 times 3 equals 65.571 plus 20 times 6 times 5. Moment arm is 5. So solving for RB left is 71.946 kilonewtons. Then considering BC, summation moment about C equals 0. So RB right times 5 la equals 65.571 plus 6.801 plus moment of this load 1 half or 0.5 of 3 times 24 times 1, where 1 is 1/3 of 3. So zero point 0.5 of 3 times 24 times 1. So RB right is equal to 21.674 kilonewtons. So adding RB left and RB right, that's the reaction at B, which is equal to 93.620 kilonewtons. Then for R sub C, considering BC, summation moment B equals 0. So RC left times 5 plus 6.801 plus 65.571 then equals moment of this loading 1 half or 0.5 of 3 times 24 times 4, where 4 is 5 minus 1 because the moment arm of the centroid or the centroid of the triangle from C is 1, so its distance from B is 4. So solving for RC left is 14.326 kilonewtons. Then to solve for RC right, considering CD, span CD, summation moment D equals 0. So RC right times 6 plus 6.801, then plus the moment at D, which is clockwise also, which is 92.289 as shown. Then equals moment of the loadings 30 times 2 plus 25 times 4. So solving for RC right is 10.152 kilonewtons. Therefore, R sub C is 14.326 plus 10.152. R sub C is 24.478 kilonewtons. Then for the slopes at A and B, so let's solve for reaction at A. Considering AB, summation moment about B equals 0. RA times 8 plus 65.571 then equals 20 times 6 times 3 plus 30 times 11. So solving for RA is 78.054 kilonewton. Let's now draw the moment diagram by parts for portion AB. So we have 78.054 reaction at A times 8 is 624.432 over EI of AB. Take note, EI of AB is 1.5I and EI is 40,000 kilonewton meter square. Therefore, 1.5 of 40,000 is 60,000. So this is 60,000 kilonewton meter square for IAB. Moment of the load, second degree, is 20 times 6 times 3, 360 over EIAB, and it is second degree. Then moment of the 30 kilonewton load, we have 90 over EI here at A, then 330 over EI AB at B. Let's divide this trapezoidal loading because we only consider this trapezoidal loading between A and B area into two triangles as shown. So the area of the triangle, this is the centroid of the spandrel, this distance is 6 over 4, 1.5. So the distance from the left is 8 minus 1.5, so 6.5. Then the area of this triangle is 1/2 of 8 times 624.432 is 2497.728. The area of the spandrel is 720, 1/3 of 6 times 360. The area of this small triangle is 360, 1/2 of 8 times 90. And the area of this bigger triangle is 1/2 of 8 times 330, so it is 1320. So let's evaluate EI division of A relative to B, EIAB division of B relative to B, EI division of B relative to A, so moment of these areas with respect to B. So 2497.728, the moment arm is 1/3 of 8, so 8/3, minus 720 times 1.5, minus 360 times 2/3 of 8 is 16/3. Then minus 1320 times 1/3 of 8, 8/3. So minus 1320 times 8/3. So simplifying, division of B relative to A is 140.608 kilonewton meter cube. So divided by 60,000, then division of B relative to A, this is in meter, so we multiply 1000 to make it mm. So the shortcut is we just divide it by 60, supposedly, to convert it to mm. So the value is 2.3435 mm, and let's draw it from the figure, the tangent. So division of B relative to A is 2.3435, and it is positive. So that means point B is above the reference tangent at A. But because this is only 2.3435 less than 5 mm, remember the vertical distance between A and B is 5 mm, so this is the tangent at A. So this is division of B relative to A. So therefore, the tangent at A is sloping up to the right, or from the horizontal axis to the tangent at A, it rotates counterclockwise. So therefore, theta A is positive for counterclockwise rotation. So let's have it clear here. This is A, this is B. This is the tangent at A, and this is the division of B relative to A, which is 2.3435. And since the vertical distance between A and B is 5 mm, so therefore 5 mm minus 2.3435 is 2.6565 mm. So this is theta A, which is counterclockwise from the horizontal. That's why it is positive. And this is 8 meters or 8,000 mm to be consistent. So that's theta A. Theta A is opposite over adjacent, and it is positive. The rotation is counterclockwise. So theta A is 2.6565 over 8,000. So theta A is equal to 3.3206 times 10 to the negative 4 radians. Let's also evaluate division of A relative to the tangent at B. So we copy the areas, then we just change the moment arms. So EIAB division of A relative to B is 2497.728, this time 16/3, 2/3 of 8, then minus 720 times 6.5, then minus 360 times 8/3, that's 8/3, and minus 1320 times 16/3, so 2/3 of 8, 16/3. So computing division of A relative to B is 641.216. We divide it by 60 to change it to mm, and it is equal to 10.687 mm. Because division of A relative to B is positive, that means if we draw tangent line from B, and A should be above that reference tangent, so it should be here as shown in the figure there, and also here. So A is above this reference tangent at B, and this distance is 10.687 mm, and because this is 5 mm, therefore this is theta B. Theta B again is the tangent at B is counterclockwise from the horizontal, therefore it is positive. So theta B is opposite, which is 5 plus 10.687 divided by adjacent 8,000. So theta B is 5 plus 10.687 divided by 8,000. So theta B is equal to 1.9609 times 10 to the negative 3 radians. So I hope that I presented the problem clearly, and I hope that we were able to follow the solutions.